So, welcome back to this problem solving session on the course Introduction to Abstract and Linear Algebra. Today we'll discuss questions related to week 8 of the course. Okay, so we'll start with this first question. So we have an invertible matrix P and a diagonalizable matrix A. So then which of the following is true? Okay, so just that I would like to just give me 1 minute. There's some- Yeah, sorry. So, uh, so we'll start with this question. I'm really sorry for that. Yeah. So, just that I would like to rephrase the question. So, if A is a diagonalizable matrix, then for some invertible matrix P, which of the following holds true? Right? That would be a better way of answering the question. So, does anybody want to guess an answer? Deeply, would you like to explain your answer? You can unmute and speak. What is the option C say? A power n. Okay, so you're right. So what do you mean by A is diagonalizable? So A is just the definition, or what it means is there is some invertible matrix P such that P A D inverse is a diagonal matrix. So D is a diagonal matrix. Although it's not mentioned in the question, that's what D means. Now, see, one advantage of having of knowing the information that the matrix is diagonalizable is that if you want to raise it to some powers, things become very easy. So that's the probably the point of the question. Because you look at, suppose you want to compute a power n, and a is some random matrix, it will be very hard to compute, right? Even if you want to write a program or whatever. But once you know that it is diagonalizable, now you look at it. Let's do PA, P inverse. Uh, question is asking the other way. Yeah. So you take P to the other side, you have A is P inverse D into P. And P, if P is an invertible matrix, then P inverse is also another invertible matrix. Maybe to keep it consistent with the notations of the question. Equal to D, you take Q to the other side. So you have Q inverse D Q. Now, you let P be Q inverse. So you get P is P B P. Now let's see what happens when you raise it to some power. Right? So you have A power n is P D P inverse whole power n. So let's just look at what happens P D P inverse the whole square. What is this? P D P inverse into P D P inverse. So this P inverse gets cancelled and we get
Again two different ways.
sorry. Okay. So this becomes P D square P inverse, right? So in general, if it is power n, this will actually become P D power n P inverse. So the point is that once you know this P, the invertible matrix which makes A into D by this kind of a map, computing any power of A becomes very easy. See, computing the power of a diagonal matrix is very easy, right? So you have 1, 0, 0, 3. So if you take power n, you can multiply and see this will just be 1 power n, 0, 0, 3 power n. So computing this d power n is easy, and knowing that something is diagonalizable makes the computation of its powers also. I hope this was clear. Any questions? So you are right. The answer is we'll move on. Yeah. So the next question is this. Which of the following is true? Sum of eigenvalues equal to the trace. This we already saw last time. And the next one is eigenvalues of a matrix and its transpose are same because the transpose matrix will have the same characteristic equation. So this is also a true statement. So basically, we get that both of these are statements. So okay, one way of proving, if you want to look at a proof, you can show that determinant of A is equal to determinant of A transpose for any matrix A, and that will give that determinant of A minus xi is equal to determinant of A transpose minus xi transpose of xi. For the way. And that will give that eigenvalue. Okay. So this one, you have a 3 cross 3 matrix A. One, two, and 4. So the question is, what is the determinant of A inverse transpose? Yeah. This, does anybody want to answer? Any guesses? Uh, see.
Option E.
Okay, that's the answer, but can you tell how you got it?
Actually, inverse of a
Mm-hmm.
matrix A, the eigenvalues are 1 by 1, 1 by 2, 1 by 4. The transpose have the same eigenvalues. That's why the product of eigenvalues is a determinant of A inverse transpose. So 1 by 8 is the answer. That is 0.125.
Perfect. Now, let me write what you are saying. Um, so, if A has eigenvalue lambda, then 1 by lambda will be an eigenvalue of A inverse, right? So this is not very difficult to see. So if you look at the class notes, one way of one way of looking at eigenvalue is it's the roots of this characteristic polynomial. Another way of looking at it is, so when is lambda said to be an eigenvalue of A? So to be an eigenvalue of A if there exists a non-zero vector x such that Ax equal to lambda. Right? Now you multiply by A inverse on both sides. So see, first of all, lambda cannot be 0. This we saw last time, that eigenvalues of an invertible matrix cannot be 0. So since eigenvalues of an invertible matrix cannot be 0, lambda is not equal to 0. Yeah, so you multiply by A inverse, multiply equation 1 by A inverse. So what we get is A inverse Ax is equal to A inverse times lambda x. So this becomes identity equal to, lambda is just a scalar. So I can write it as lambda times A inverse x. And you take lambda the other side, because it is non-zero, you get 1 by lambda times x is equal to A. So this proves the statement that if lambda is an eigenvalue of A, 1 by lambda is an eigenvalue of A inverse. So now you go back to the question. We know that 1, 2 and 4 are eigenvalues of A. So what will be the eigenvalues of A inverse? So 1, 2, 4 are eigenvalues of A. 1 by 1, 1 by 2 and 1 by 4 are eigenvalues of A inverse. So now you use the fact that any matrix and its transpose have the same eigenvalue. So what we get is eigenvalues of A inverse transpose are 1, 1 by 1 is 1, 1 by 2 is 0.5, 1 by 4 is 0.2. And determinant is product of eigenvalues. When you take the product of these three values, you get 0.1. Is this okay? Any questions? There are no questions. Go ahead. Let A be an n cross n matrix of rank n. Any matrix similar to A. So what do you mean by a matrix similar to A? Yeah, what is the meaning of a matrix being similar to A?
There exists a non-similar matrix C such that A equal to CA C inverse.
Characteristics polynomial are same for both.
Yeah, that is true. Characteristic polynomials are same, but just because two matrices have the same characteristic polynomial doesn't mean they're similar. Yeah, CA C inverse is right. So basically, let's say B is similar to A means that there exists an invertible matrix let's call it B such that B is PAP, right? So, okay, let me finish this question and then. So yeah, whatever you said, observation is right. If two matrices are similar, their characteristic polynomials will be same. So that is easy to see. Like, what is the characteristic polynomial of A? It is determinant of xi minus A or with B, the determinant of xi minus B, which is determinant of xi minus B. You can write it as PAP inverse, and so this identity also we'll write it as PP inverse. That is equal to, so determinant splits. Determinant of AB is equal to determinant of A into determinant of P. So this, what we'll do is, we'll write it as P times, we're taking P common on the left side and P inverse common on the right side. So this is determinant of P into determinant of xi minus A into determinant of P inverse. And this determinant is nothing but scalars, right? They are numbers in the field. And also another factor is determinant of P inverse is 1 by determinant of P. So that gives that this is equal to determinant of xi minus A. So here we have used the fact that determinant of P inverse is equal to 1 by determinant. So they have similar matrices have same characteristic polynomial. That is. But the question is, what about the rank? Right? So one thing is, you take any matrix, you multiply, post multiply on the left, right, with an invertible matrix, the rank doesn't change. So this is something that you can check. Let A be any matrix. So you can take, M cross N. It need not, we have not even specifying that it's a square matrix. And so let P be invertible cross N matrix, and let's say U is an invertible matrix. So rank of A will be the same as rank of PA, which is same as rank of AQ. So you multiply on any side by an invertible matrix, the rank doesn't. Right? So using this, we get that the rank of similar matrix. So when you say similar matrix, you're multiplying both sides by an invertible matrix. So the rank will remain. Is this okay? So again, in this question, there may be an ambiguity that the rank is less than or equal to n, but let's say this is the best fit, most appropriate. Yeah. Are there any questions? Okay. So,
Ma'am, to get a similar matrix, we need to multiply with the matlab, how to get a similar matrix there?
this one. So you take any invertible matrix. Okay. See, suppose you have a matrix A and you want matrices which are similar to A. So what will you do? You take any invertible matrix and you multiply it like this. So PA, P inverse.
Okay, got it.
Any more questions? Okay. So if there are no questions, let me ask or say something. So we saw linear transformation, right? So this is just a digression. So we saw linear transformations, right? So and we saw that if you have a basis and a linear transformation, we can get a matrix out of it. So let's say V is a vector space, P is a linear transformation from V to B, and we have some basis. So B. We saw that given a basis, there is a way of writing a matrix associated to T. Right? So we'll call this, we'll denote it like this, is the matrix of T with respect to the basis T. So if you don't remember how we did it, maybe we'll look at one question. So after finishing this, but just recall that there was a way of associating a matrix to a linear transformation given a base. Okay. So now the question is there an interpretation of this similarity of matrices in terms of linear transformation? Right? Is the question clear? So what we have is we have linear transformations. Like let's say set of all linear transformations on one side from V to V, and we'll assume that dimension of V is let's say n. So given a basis, via a basis, we were able to associate an n cross n matrix. So when we do this, there has to be some meaning or some need to do it, right? So the question is, here we have the concept of similar matrices. So what does this concept translate to here? Has anybody seen it before, read it somewhere, or so this is a slight digression from the problems. So it's okay if you haven't seen it. It's just something interesting, so I wanted to say. Anybody wants to comment? Or at least you can take a guess. It's okay if it is a wild guess. Okay, sir. Okay. So, so what happens is here when you take similar matrices, so what did we see? We have a linear transformation and you fix a basis, you're getting a matrix, right? So this taking similar matrices actually corresponds to changing the basis here. What I mean to say is, so you have this T from B to B and suppose we have two bases. One, this is a basis of B and we have another basis. Like I hope you have seen that a vector space can have multiple basis sets. This is another basis of B. You take the matrix of T with respect to B1 and you take the matrix of T with respect to B2. How will these two matrices be related? They will actually be related by the similarity. So, which means that so there will exist an invertible matrix P such that one will be P similar to the other by this via this matrix. So that is the picture on the other side of the story. That's what it means in terms of it's okay if you haven't understood it completely because they've not given the proof of it. But yeah, this is what is actually happening. Okay. Any comments, questions?
No, ma'am.
Okay. So we'll move on to the next question then. So if minus 4.5 minus 4, 1 is an eigenvector of this matrix, then the eigenvalue corresponding to this eigenvector is. So again, let's recall if you have a matrix A. So B is said to be an eigenvector of A. An eigenvector of A corresponding to an eigenvalue if it satisfies AV equal to lambda. So here our matrix is eight minus 4, 2. So this is our matrix times the vector B. Let's compute that. Yeah. Anybody has computed it? You can take a minute or two to compute it. It's just multiplying matrix. Is it taking that much time or is it? Okay, forget computing the whole thing. Just the first entry or any one of the
Minus 18. First entry minus 18.
So, see, okay. So the remaining entries, I'll just tell you what it is. This is what it is. But
Minus soul and 4. Yeah.
yeah, but even before you compute the whole thing, once you know that this is an eigenvector, what do you know that this new vector that you obtain, this should be some multiple of this original vector, right? So this is the blank that we are trying to do. Minus 4.5 minus 4, 1. So when if you are already told that this is an eigenvector, you don't even have to compute all the three values to just get the eigenvalue. Just the first entry will tell you, what is the eigenvalue. But anyway, so this will be what 4 times minus 18 minus 64 is 4 times this vector. So the eigenvalue corresponding to this eigenvector is 4. Is that okay?
Okay, ma'am.
Okay. So we have a lot more time. If you have any questions, you can ask. Otherwise, maybe I'll discuss some other questions. Any doubts? You can, if you want to ask anything related to anything that happened in the course or something. If not, then do one question. Let's do one question which will bring in a lot of concepts. So, we have a linear transformation. Okay, from R3 to R3, and this is like P of A1, A2, A3 is 4A1 plus A3, 2A1 plus A2 plus. So the question is, what are the eigenvalues of P and what are its corresponding eigenvalues? So, what does eigenspace mean? That once you get an eigenvalue, uh, you look at all which are eigenvectors corresponding to that eigenvalue. That is the eigenspace. This is if lambda is an eigenvalue of, let's talk about matrices of a matrix A, then eigenspace corresponding to lambda is all those eigenvectors corresponding to the eigenvalue lambda. So it is a set of all V in the vector space V such that AB equal to lambda. This is okay. So what is this question asking you to do? So you know how to compute eigenvalues, eigenvectors of a matrix. You have a transformation. So what you do is you take a basis, write the matrix of this transformation with respect to that basis, Then compute the eigenvalues and eigenvectors of that matrix. Is this okay? What we are going to do, is that clear? So it involves a lot of things, and I think in a way it will also go through a lot of concepts that were covered in the at least last few classes of the course. Is this okay? Any questions? I mean, any questions about the question? Sorry. I wasn't able to understand it. Okay.
When did the battle started? How long did it travel?
If you're not
Battles.
yeah. So the first task is,
Ma'am, can you explain it again?
sorry, what do you want me to explain? Which part of it? Yes, please. You can unmute and ask your question. I heard someone say, can you explain it again? I just want to know what you want me to explain. Maybe the question, I'm guessing it's the question, so I'll do it again. See, you have a linear transformation from R3 to R3, right? And the question is, what are the eigenvalues of this transformation and what are the corresponding eigenspaces? Okay, so for now, forget about the linear transformation. You just understand what is eigenvalues and what is eigenspace. So what is an eigenvalue? Given a matrix, you find its characteristic polynomial, you find the roots of the characteristic polynomial, that will give you the eigenvalue. And what is eigenspace? Once you find the roots of the characteristic polynomial, you take every root, right? You go to individual roots. So let's say lambda is a root, that is called an eigenvalue. So corresponding to lambda, you look at all the vectors which satisfy this equation. AV equal to lambda v. So you collect all the vectors, it will be a set, in fact it will be a subspace. You can show that it will be a subspace. That is called the eigenspace corresponding to lambda. So for a matrix, you know what is eigenvalues, you know what is eigenspace now. Now what we have is a transformation. So what we'll do is, we have seen how to move from transformation to matrix. Given a linear transformation, how do you write a matrix corresponding to it? So what we'll do is, corresponding to this transformation, we'll write the matrix, and for that matrix, we will compute the eigenvalues and eigenvectors. Is this okay? Or are there any more questions?
Proceed, ma'am. Okay.
Okay. So we have this transformation. The first step is choose a basis. B and write the matrix of P with respect to this basis. So since it is R3, the easiest basis we'll take, if I mean whenever we have a choice, we would like to choose the easiest one, so we'll just choose the standard. Right? So how do you write? So the first thing is, you understand how do you write the matrix of P with respect to this basis. So what you do is, you find P of each of these basis vectors. So you find T of 1, 0, 0, T of 0, 1, 0, 0, 0, 1. So the map is given by A1, T of A1. You can just note it down somewhere. I don't want to keep coming here. T of A1, A2, A3 is given by this. So we'll compute this for E1, E2, E3. Okay. So T of E1 is 4, 2, 1. Okay. So your A1 is 1, A2 and A3 are 0. So you just substitute the values, you get 4, 2, 1. And T of A2 will be 0, 3, 0. T of A3 is 1, 2. Okay. So once you compute this, how do you write the matrices? Whatever is your output, like whatever is your T of 1, 0, 0, this you have to write it as a linear combination of the bases. Since we are doing standard bases, writing this will be very easy. So you write these values as a linear combination of the bases vector. So this will be 4 times 1, 0, 0 plus again, I mean these numbers are turning out to be the same because it's a standard basis, but this is an important step. Plus 1 times 0, 0, 1. So this is what? 0 times 1, 0, 0 plus 3 times 0, 1, 0. That's again 0 times 0, 0, 1. And finally 1 times 1, 0, 0 plus 2 times. Yeah. Now these coefficients that you get, you write it as a column. Okay. So matrix will be, we usually denote it like this. 1, 2, 4 coming from the green underline thing. 0, 3, 0 is coming from the blue coefficient and this is coming from this. So the first thing is done. We have found the matrix. The next task is find eigenvalues of this. Okay, for simplicity, let me call it A. So find eigenvalues of A. So how do you find eigenvalues? Which is nothing but roots of the characteristic polynomial. So how do you find the characteristic polynomial? It is nothing but determinant of xi minus a. So that would be determinant of minus 4, 0, minus 1, minus 2, minus 3. So we will skip the computation and just write the answer. So this will turn out to be t minus 5 into t minus 3 the whole square. Okay. So you can just check this later. The variable is x minus 5 into x minus 3 the whole square. Yeah. Once you know this, now you know what are your eigenvalues. So find the roots of these equations, which are 5 and 3, are so 5 and 3 are eigenvalues of A. Once you are done with this, the task is for each of these eigenvalues, you find the eigenvalues. eigenspace eigenvalue. So let's start with the first one. So let's start with eigenvalue 5. So how do you find the eigenspace? So what is eigenspace? It's all those vectors which satisfy. So eigenspaces, basically we want to find any questions. Yeah. So you want to find all the vectors v such that a times v is equal to 5v, right? Or in other words, a minus 5 times identity v equal to 0. So the reason the second one is easier to find is we have seen how to solve linear equations. So it's easier to find vectors which satisfy the second equation. So maybe I'll just do one eigenvalue. You can try the other. So what is our A? A minus equation. So A minus 5 times identity would be minus 1, 0, 1, 2, 3 minus 5 minus 2. Is this okay or should I actually write it out what it is? I mean, A times A minus 5 times identity is nothing but A minus 500,050,005. So which means each of the diagonal entries you're subtracting 5. That's what you're doing to get the matrix. Okay. So now you're trying to find so all the vectors which satisfy this, right? So what you want is all x, y, z such that minus 1, 0, 1, 2, minus 2, 2, 1, 0, minus 1 times y, z equal to 0, 0, 0. So this is high school solving equations, linear equations, system of linear equations. So what will this be? Minus x plus z equal to 0, 2x, 2y plus 2z equal to 0. The last one is minus z equal to 0. That's it. So this last equation is just the negative of the first one. So this is not really needed. So essentially we just have two equations. And if you remember one thing, that whenever the number of equations is less than the number of unknowns, you will always have a solution which is non-trivial. See, if you look at this system, x equal to 0, y equal to 0, z equal to 0 is always a solution. But if the number of equations is less than the number of unknowns, you will have a solution apart from this trivial solution. Okay, anyway, so this is discarded. So we just have two equations. So basically one variable we have a choice, right? The other variables will depend on that. So the first equation gives x is equal to Z.
Ma'am, your rank of A is to be is
Did we lose the connection?
Ma'am,
The voice is not audible.
Oh, yeah. Is it okay now?
Yes, ma'am.
Yeah, yeah. Thank you. Yeah, I'm so sorry. It is some Wi-Fi issue. So, somebody was saying something about rank, right? So, I didn't hear it completely. Okay, so substitute in 2. So what we get is 2z minus 2y plus 2z equal to 0, which is 4z equal to 2y is 2z equal to 1. Right? So once you fix the value for z, x and y are defined. So what will this vector be? So this the solution to this equation or the eigenspace corresponding to the eigenvalue I.
1 to 1.
Sorry, sir. So you fix z and then you know what x and y have to be. So y is z by z is the real, right? So So if you look at the last week's content, sir has defined two numbers. One is algebraic multiplicity of an eigenvalue and geometric multiplicity of eigenvalue. So algebraic multiplicity of an eigenvalue is the number which comes here. If you look at the characteristic polynomial and an eigenvalue, how many times does it appear as a factor in the characteristic polynomial? And geometric multiplicity was defined to be the dimension of the space, of dimension of the eigenspace. So here you can say that algebraic multiplicity of phi equal to geometric multiplicity of phi is equal to 1. So similarly, you can do the eigenspace corresponding to 3. It is the same computation. Should I do it or I could try it on your own? Okay, is there anybody who wants me to do it? Yeah, anyone who wants me to do the computations? It's very similar to what we did for 5.
Yes, we can do it.
Okay. So again, it's the same thing. What do we have to find? We have to find all those vectors such that A minus 3 times identity times vectors B equal to 0. So,
Then you write direct vectors.
okay, you want me to write it out directly? Okay, so it will be so the equations will turn out to be 1 second. Did I make any? Y is 2z. So,
Then we can do it.
yeah. Sorry. Okay. So for this, the equation will turn out to be you'll end up with just one equation, x plus z equal to 0. So there are a lot of steps skipped here. I just say do computations similar to the previous case. Right? So your eigenspace will actually be minus z. Y doesn't have any condition, and yeah. So this is a two-dimensional subspace. So again here your algebraic multiplicity is of 3 equal to geometric multiplicity of 3, which is equal to 2. Right? And one of the conditions for diagonalizability of a linear transformation was that these two numbers have to be equal for every eigenvalue. Okay? So one of the conditions for diagonalizability of P was that algebraic multiplicity equal to geometric multiplicity for every eigenvalue of P. So in our case, we see that this is happening, which means that this matrix, or if you associate it with a linear transformation, the transformation is actually a diagonalizable. It's a diagonalizable matrix and a diagonalizable linear. So that's P, and consequently the matrix that we associated with P, which we called as A, are diagonalizable. Okay, we'll stop with this. If you have any questions, you can.
This will be the last session or session is planned?
So officially this is the last session. There is a possibility that we'll have one more session to revise everything, but it has not yet been confirmed. If
When
the
it will
team
be?
confirms it, I have no idea. That is decided by the NPTEL team. If they do decide to have one, they'll announce it for us.
Excuse me, ma'am.
Yes, please.
How many questions are given in final exam?
I have no idea about the exams. You can ask the official PA of the course.
Okay, ma'am.
What's
Thank
the-
you, ma'am.
And these vector should be linearly independent, no?
Sorry, sir, can you repeat your question?
These
Ma'am, only
vectors,
objective type now.
I have no idea about the exam or anything related to technical part of the course. You can either mail the coordinators or ask in the special program.
and these vectors should be linearly independent.
Which
Is it-
vectors?
Of these vectors, eigenspace.
Yeah, so I think one theorem that you've already proved is if you have two different eigenvalues, then the eigenvectors of those eigenvalues will be independent. So that has been done in the course. And in eigenspace, within the eigenspace, when we say it has dimension 2, that itself means that there are two linearly independent vectors, right? That's what dimension means. So just the fact that we're saying that geometric multiplicity is 2 means that there are two independent vectors. Here we have one independent vector, and since this vector and these two vectors are corresponding to different eigenvalues, they will be independent. So if you just look at the class notes, yes, sir has actually proved that this fact. So using that, we'll get that all of these three vectors are independent. So all of these information actually goes into this result. I hope that answers your question. Any more questions?
And is it necessary and sufficient conditions for diagonalizable
Yes, yes.
to be the algebraic multiplicity should be equal to geometric multiplicity?
Yeah,
It is sufficient.
It is
It is
sufficient.
sufficient condition or it is both
Both.
necessary and sufficient?
It is necessary and sufficient.